Welcome back to The Explainer. Okay, today we're diving into a really high voltage neon lit journey that's going to completely change how you look at the physical world around you. Seriously. We're going from the fundamental, indestructible Lego bricks of the universe all the way to the absolute cutting edge where AI supercomputers are literally designing our future atom by atom. And look, this isn't just theory. This is the exact chemistry powering the screen you're staring at right now.
So let's start with a quick thought experiment. I want you to reach into your pocket, or, well, maybe you're holding it right now, your smartphone. It just feels like a solid, smooth piece of glass and metal, right? But I want you to guess how many fundamental ingredients of the universe are sitting right there in the palm of your hand. Just think about it for a second. Is it 10? Maybe 20?
Well, if you guessed somewhere in the 20s, you might be thinking of way older technology. Because the answer for a modern smartphone like a new iPhone is a staggering 63. Yeah, 63 different elements from the periodic table are packed into that little device. Your phone isn't just a gadget, it's an absolute chemistry revolution right in your pocket. It's this precisely engineered masterpiece of matter. But here's the thing, how do we actually power that masterpiece? Every single time you plug your phone into charge, you're essentially lighting a fire. Now, obviously you don't feel the heat, but the electricity flowing into your battery is the direct result of combustion and energy transfer happening somewhere down the line, usually at a power plant. The massive energy demands of all this modern tech mean we're constantly wrestling with these chemical reactions just to keep our lives running. So to really understand how we design the future, we kind of have to look at the very foundation of reality itself. Which brings us to part 1, the universal Lego bricks. The absolute crucial point here is the atom. Think of atoms as literally the ultimate Lego bricks of the universe. Just like, physical Lego sets have really specific types of pieces, our universe has 118 distinct element types. And these are all laid out nicely on the periodic table. From the carbon in our bodies to the gold and silicon inside our electronics, everything around us is built by simply rearranging those 118 fundamental building blocks. But combining these bricks, that changes everything. Take pure carbon, for example. That's just one element. It could be graphite in a pencil or even a super tough diamond. But mix that exact same carbon with hydrogen in a very specific ratio, like C25H52, and suddenly you have soft candle wax. Chemistry is really just the study of how matter and energy interact when we snap these different elemental bricks together to create completely new things. So what actually makes these bricks interact in the first place? Well, it all comes down to chemistry's most basic rules. Protons in the core, they tell you exactly what the element is. But the electrons orbiting the outside, they're the ones doing all the heavy lifting. They completely drive the chemical reactions. You see, all that chaotic energy powering our electronics basically boils down to electrons trying to find a stable home. They're desperately trying to mimic the perfectly balanced configuration of noble gases. That interaction between positive and negative charges is the exact thing that creates the flow of power we rely on every single day. Moving on to part 2, the age of atomic design. All right, so we know the rules of the Lego set. Now let's see how this actually scales up into human history. Historians love to name human eras after the materials that totally define them, right? We had the Stone Age, the Bronze Age, the Iron Age. And then, more recently, that incredible processing revolution gave us the Silicon Age, where it suddenly became cheaper to print a transistor on a chip than to print a single letter in a newspaper. But we're moving past that now. We aren't just finding materials in the dirt or printing circuits anymore. We are in a completely unique era. We're actually designing matter, atom by atom, exactly how we want it. Which leads right into part 3, building better batteries. So one of the absolute most practical and urgent applications of this new atomic control is solving our massive energy bottlenecks. Enter this groundbreaking class of materials called superconducting organic polymers, or SOPs. Now, I know that sounds super complex, but the concept is just fascinating. These are engineered carbon-based materials, specifically pi-conjugated architectures, right at the nanoscale, that can actually conduct electricity with almost zero resistance. Imagine a high-speed, completely frictionless superhighway for electrons, allowing power to flow freely and incredibly efficiently without generating all that wasted heat. And it gets crazier when you combine these SOPs with specific nanoparticles. You get these incredibly powerful hybrid composites. We are literally talking about creating intelligent materials. Think smart cement or smart coatings that can actually self-monitor their own structural health, harvest solar energy, and actively adapt to their environment. This kind of atomic-level synergy is absolutely set to revolutionize how we build our entire infrastructure. So, how does this actually apply to the battery sitting in your phone? Well, material scientists are using these exact atomic-level steps to optimize modern energy storage. Step 1. They synthesize specific nanoparticles, things like cobalt oxide because it has a huge energy capacity, and graphene for ultimate conductivity. Step 2. They blend those perfectly with our high-speed superconducting organic polymers. And step 3, they integrate that hybrid matrix directly into highly efficient lithium-ion batteries. By super carefully managing how those charges separate and interact at the nanoscale, we're drastically preventing energy loss in the devices we use constantly. It's a real game changer. And finally, part 4, AI and future chemistry. Now, designing these complex hybrid materials takes immense precision, obviously. But the crazy part? We aren't just relying on old-school trial and error in the lab anymore. We're undergoing this massive fundamental shift. See, traditionally, discovering a new catalyst or a much better battery material took decades, literally decades of painstaking trial and error. Mixing things, testing them, failing, and trying again. But today, with AI-driven methods, by using deep learning and large language models, we can predict molecular behaviors and screen candidates virtually in just a matter of days. The difference in speed is simply staggering. Think of it like this. It's basically AI playing with those universal Lego bricks in a massive virtual playground. Machine learning algorithms can screen millions of potential compounds instantly. Graph neural networks jump in to map out the exact atomic structures and predict exactly how they're going to react. And honestly, the most amazing part? Generative models can perform what's called inverse design. Basically, you give the AI a desired property you want, and it designs an entirely new molecule from scratch just to meet that need. It completely bypasses all those computationally slow quantum mechanics calculations and discovers new materials totally autonomously. No way we could do that manually. Decades ago, the legendary physicist Richard Feynman famously said, "There's plenty of room at the bottom to put atoms anywhere we want." For a really long time, that was just a prophetic dream. Kinda sci-fi. But today, thanks to this incredible convergence of material science, advanced chemistry, and artificial intelligence, that dream is an absolute reality. The ultimate level of atomic control is happening right now, today, in labs all around the world. We've moved from simply finding raw materials in the dirt to deliberately constructing them, atom by atom, aided by the sheer computing power of AI. We have officially cracked open the universal Lego set, and we're learning exactly how to snap these elements together to completely optimize our world. So the question I want to leave you with today is this. Now that we finally have the ultimate tools to design reality from the ground up, what should we design next? Thanks so much for joining me on this explainer, and as always, keep questioning the world around you.